remembering about inverse functions, we realized that if I had a function and an x to an output of y, and I wanted to try to find a inverse function that would be the input of that y and bring me back to my original starting point x, I needed a special type of function in the first place to be able to get that inverse function. And when looking at that, we found out that in order for a function to have an inverse that's also a function, my original function has to be 1 to 1. So that means that not only for every x there's only one y, but for a function to have an inverse that's also a function, for every y there's only one x. Now, when we looked at functions in general, and we saw that maybe there were some functions that weren't 1 to 1 over the implied domain, but we could restrict the domain over a span where the function was 1 to 1. We could find an inverse function for that function over that restricted domain, turning into a restriction on the range. And all of that is presented in a video on inverse functions. But I want to take those ideas and bring them to our trig functions. See, trig functions, when we think about them, and I've just done 3 of the 6 trig functions, but they are not 1 to 1 miserably. For each x, yes, there's only one y, but for each y, there are infinitely many x's over the y values that the function does attain. So I can't find an inverse trig function over the entire domain of the original trig functions. I have to think, what restriction on the domain of the original trig function would make it where that trig function is 1 to 1 over that restriction, and I also have it where I've seen all of the outputs that that trig function would have. Well, if I look first at just the y equals sine x function, and I think if I just tried to look by going right of the y-axis, notice I have a 1 to 1 function for a while, but it's still attaining some y values, but right when I hit pi over 2, it starts to come back down where it would fail the horizontal line test and not be 1 to 1 anymore. So I need to make sure I don't look at it past that pi over 2 angle. And then that's only given out positive values of y. So if I then look left of the y-axis, I see I'm still having it where it's 1 to 1, and I'm still having it where there's new outputs that I hadn't seen before. And right when I get to an angle of negative pi over 2, it starts to turn around and fail being 1 to 1 after that. So for my y equals sine x, if I restrict my domain of my angles to be from negative pi over 2 to pi over 2, then over that span centered about the origin or close to the origin, we have that my function is 1 to 1, so I will have an inverse that's also a function there. Now, how do we find that inverse? Well, if you'll recall, the first thing we do is to find the inverse. We switch the x's and y's. So we write x is equal to sine of y, even in the restriction. So negative pi over 2 is less than or equal to y is less than or equal to pi over 2. So restriction on the domain of the original function ends up being a restriction on the range of the inverse function. Now, once we looked at switching the x's and y's, the next thing we're supposed to do is solve for y. To solve for y, I write this as the inverse sign. So inverse sine of x is equal to y. And I can write that with the inverse function notation. Remember, this is what undoes what the original function did. It's not a -1 exponent used in this context. In this context, it's used as the inverse function notation. And also note that my y is an angle. So the y is equal to an angle, so the inverse sine of an argument is an angle that you get out. Trig functions, angles went in, ratios came out. Inverse trig functions, ratios go in and angles come out. So I can write this either as y equal the inverse sine of x, or another notation is y is equal to arc sine of x. Two different notations for the same idea, but I have to remember that the restriction on my domain ends up being a restriction on the range of my inverse function. So the angles that I give as answers have to be from -π/2 to π/2. Now, if you think about the unit circle, then when I'm looking at the inverse sine of a ratio, you can think what angle has the sine ratio of that argument over the span of angles from -π/2 to π/2. And if you're looking back at the unit circle to try to read that in reverse, looking at the y coordinates of the ordered pairs on the unit circle and finding the angles that that went with, then you're looking at the unit circle from -π/2 to π/2. So you're looking at the angles in the first quadrant when you're doing the inverse sine of a positive ratio, and you're going to give angles in the fourth quadrant reaching down and around if you're doing the inverse sine of a negative ratio. Now let's see what happens with our work with finding the inverse cosine function. So here's the original picture of the cosine function. Again, it does not pass the horizontal line test to be a one-to-one function. It does pass the vertical line test to be a function, but for a function to have an inverse that's also a function, it has to be one-to-one. So it has to pass the vertical line test to be a function and the horizontal line test to be a one-to-one function. Now I can't use the same restriction that I did for the sine function because it won't be one-to-one for the cosine function there. So I don't want to look left of the y-axis for this one. I actually look as I'm pulling my hand across until I hit pi, and then it starts to come back up. So the restriction on the cosine function is that my angle is between 0 and pi. And it doesn't hurt to put what the range of the function is for cosine, which also would have been the range for sine. That's from -1 to 1. So then now for my inverse cosine function, we switch the x's and y's. So x is equal to cosine y, where 0 is less than or equal to y is less than or equal to pi, and -1 is less than or equal to x, which is less than or equal to 1. Then we solve for y. Y is equal to the inverse cosine of x. The input for the ratios for inverse cosine have to be a ratio from -1 to 1, and the output for the inverse cosine has to be an angle from 0 to pi. So now with this, if I look at what angles I'm going to give back as answers for the inverse cosine of a ratio, 0 to pi, if I'm going to read my unit circle backwards, is 0 to pi. So if I take the inverse cosine of a positive ratio, I will have an angle that I give back in the first quadrant. But if I'm working on an inverse cosine of a negative ratio, I'll give my angle back in the second quadrant. And then always remember about your reference angles to be able to give those back out appropriately. And then lastly, with y equal the tangent function. So again, if I want it to be where it is 1 to 1, I'm not going to want this other branch. So my restriction on the domain of the tangent function is between negative pi over 2 and pi over 2. I can't use the endpoints because the tangent function has asymptotes there. The output for the tangent function goes negative infinity to positive infinity. So then my inverse tangent, I will switch the x's and y's. X is equal to the tangent of y, where my y is between negative pi over 2 and pi over 2. And my input ratios are anywhere from negative infinity to positive infinity. And then solving for y, y is equal to inverse tangent of x, or y is equal to arctan of x, whichever notation you want to use. And we could have done that for our arc cosine of x as well. And then again, when I think about the angles for this, if I'm thinking of the unit circle and reading it backwards, but I'll have an open circle at negative pi over 2 and an open circle at pi over 2. So we will be looking at the inverse tangent of a positive ratio is a quadrant 1 angle. An inverse tangent of a negative ratio is a quadrant 4 angle that you reach down to get. You can't go around and get it, or else it's over here instead of being right in that specific restriction that we had to do to form our inverse trig function.